Welcome back, Physics 30. This is section FM2.8, problems involving friction and inclines. So up until this point, we haven't been looking at friction. We've been assuming it's negligible. So this section takes a look at friction and how it comes into play with various forces. So use three-body diagrams and Newton's law of motions to solve word problems involving friction and objects in motion, including in plane situations. So friction. So up until now, we've ignored friction, but it must be taken into account in most practical situations. So here on Earth, we always have friction. We can't get around friction, so we have to consider it. Sometimes it's a lot of friction. Sometimes it is a small amount of friction. For example, an ice or a puck on an piece of ice. Sometimes we assume it's negligible because it's little, but it is still there. So friction exists between two solid surfaces because even the smoothest surface is quite rough. So even if we had like a flat box on a table, even though it may slide across, you can take a look here and it does appear that there are rough edges and they kind of overlap. So if you imagine it, if this is a tabletop and if this is a box, kind of the bottom of the box, if you were to look at it, would be rough like that. The tabletop also rough, and these jagged surfaces kind of interlock with each other. Okay, so it prevents it from sliding because they interlock. So when we try to slide an object across a surface, these microscopic bumps impede the motion. Even when a round object rolls across the surface, there's still some friction called rolling friction. So rolling friction due to a spherical shape moving down a flat surface, although it's generally much less than when objects slide across the surface. So we'll take a look at two different types of friction here. First one here, kinetic friction. Now kinetic, of course, the word kinetic implies moving. So it's the friction that results due to objects moving across each other. So the magnitude and the force of friction depends upon the nature of the two sliding surfaces. So is it wood on wood? Is it rubber on ice? Is it rubber on pavement? So the nature itself determines how much kinetic friction there is. So for given surfaces, experiments show that the friction force is proportional to the normal force between the two surfaces. So the larger the normal force, the larger the friction. And of course, normal force, if you look at this diagram down here, now of course a better way to, it's decent how it's drawn, but usually we draw the free body diagrams like this, right? So we draw FG pulling downwards, and normal force, the force that the table exerts back on the box. And if it's a scenario like this in which we may have something pulling this way, I'll call it FA for applied force, and friction working against the applied force. If I don't have any other angled forces, of course FG and FN will be equal and opposite, such that Fn is equal to Fg in magnitude, but in terms of direction it'd be negative. So if this is negative 10 newtons, this would have to be positive 10 newtons. So 10 newtons, positive 10 newtons. So that's why we say Fn is equal to negative Fg. So friction is directly, so of course the larger the weight, the larger the Fg, that's going to result in a larger Fn value. So friction is directly related to Fn. The friction force between hard surfaces in many cases depends very little on the total surface area of contact, assuming the surfaces are the same. So for example, if I have a block, I'll try to draw it in 3D here. So I have something like that, and let's say it's being pulled kind of out of the page, so it's 3D. So you can see here I'll have a, in terms of Fn, small fn in each kind of unit area, but larger surface contact. Versus if I take that block and orientate it like this, so kind of flip it up on its side, and like pull it kind of out of the page too. Here you'll see at every unit area, look above here, I have a huge Fn amount pressing down on the contact surface. So I could say this is large Fn, but smaller surface contact. So those scenarios are equal. They both result in the same amount of force. So one's compensated for the other. Small Fn but large surface contact. Larger Fn but smaller surface contact. So the contact surface doesn't change the amount of friction that's going to be applied here if I'm moving this block kind of out of the page at you like that. Okay, so it depends upon the nature of the two surfaces more than anything. If you look at the next page, so if you look here, what this means is this is the directly proportional symbol. So the force of friction is directly related. So of course that means is directly related to the normal force. Now, when changing a proportionality into an equation, we introduce a constant. In this, we usually call it little k. In this case, we call it the Greek symbol mu subscript k. So where Ff is the force of friction, and of course that acts parallel to the two surfaces. Normal force acts perpendicular, of course. And this mu k is called the coefficient of friction. And what it is, it's a number, and it's really the constant of proportionality that depends upon the nature of the two things that are sliding past each other. So if we look over here, I have a table here that kind of illustrates the value of the coefficient of friction between various substances. So again, if I look over here, mu k, if I divide each side by Fn, it's the ratio of force of friction to normal force. Of course, all of these should have, these are all vectors, of course, so they should have the half arrow. So it's a ratio that depends upon the force of friction compared to normal force. So F divided by F, newtons over newtons, so it's a unitless number. Again, it's a ratio. And of course, the larger the ratio, the larger the force of friction will be compared to Fn. So if you look over here, for example, we'll just look at this column, the kinetic, the moving friction coefficient. So wood on wood, 0.2. Ice on ice, 0.03. So you can see it's a lot less. And basically, in terms of these numbers, just simply look at them in terms of the larger the number, the larger the friction. Metal on metal lubricated, 0.07. Steel on steel unlubricated, 0.6. So you can see more friction when non-lubrication. Rubber on dry concrete, etc. Okay, so there's some values and some scenarios here that discuss the amount of friction. And of course, the next part involves this. And if you look at the scenarios here, 0.2, 0.4, 0.03, 0.1, 0.07, 0.15. This is static friction, or friction required to get an object moving. So if you look at the next page, we'll look at static friction now. Static. So sometimes it's referred to as starting friction because the word static implies at rest. So the friction to overcome to get something moving. So the values of mu s are also listed on this page. Static friction refers to that friction that must be overcome to get an object moving. As seen in the table, it's larger than kinetic friction. The reason for this is that at rest, the surfaces interlock with each other. So just like I drew on that first page here, if we have a book on a table, you can see things get interlocked. But once the object starts moving, it still has interlocked. It's not settling down and locking up. It's in a movement motion. Here we use those lines that they use in cartoons to imply that this is moving to the right, so it's not going to interlock as easily as when it's stopped. So at rest, surfaces interlock with each other, but when an object starts moving, it's more difficult to interlock them because, well, it's moving. For example, it's easier to push a car once it's moving out of the mud or out of a snowbank once it has become unstuck than when it's initially. And we've all experienced that. Pushing a car that's stuck in the snow, it's more difficult to get it moving than it is to keep it moving. The value from US can vary from 0 to a maximum number. Therefore, it's a similar equation, except here we use the less than or equal to sign. Because if an object is just sitting there, well, there is no friction. If I start pushing it a little bit, the friction is more. So let's see if I can maybe draw this. So if I have a dude here pushing, let's say that, then the FF will be that. If I push a little bit harder on a box, then the FF will be bigger as well. So it varies depending upon how big the applied force. And of course, once this gets moving, then that changes the scenario, and we'll take a look at that at this example in the next video. So the static friction force increases. Let me put a star beside here. It increases as the applied force increases. Hopefully that makes sense, because if I wasn't pushing at all, there would be no friction. So if I'm just standing here, well, there is no, I'm not applying a force, so there's no friction force. So it alters from 0 to some maximum value. So when the object starts to move, we'll see that kinetic friction takes over. And we'll take a look at that in the next video.